Hello, everybody. My name is Jacob Suchoski, and I will be presenting our work on scaled inertial forces to alter weight perception in virtual reality on behalf of myself and my co-authors, Susana Martinez and Allison Okamura. So we're interested in providing haptic feedback in virtual and augmented reality. In scenarios where people train for manipulation tasks in virtual environments, it stands to reason that compelling, realistic haptic feedback will help them transfer what they learn in the virtual environment to the real world. In current virtual reality systems, the user's hands are tracked, but when manipulating virtual objects, one only feels one's fingertips touching each other. Traditional haptic force feedback devices are world-grounded and often desktop-based, and they impart forces on a user through a manipulandum. Another approach is user-grounded devices, such as exoskeletons. These kinesthetic feedback devices apply forces to the user over one or more joints. The device pushes on the user, and the user can actively resist or oppose the motion. However, these devices are difficult to integrate with virtual and augmented reality. Such devices have workspace limitations, increased friction and inertia that come with increased size, or, for exoskeletons, are difficult to fit for a wide range of users. In contrast, wearable cutaneous devices do not have the same limitations. Our question is, can cutaneous feedback devices be as realistic and provide the same type of experiences as these kinesthetic feedback devices? There's a class of cutaneous devices that deform the skin in order to provide feedback. Such skin deformation feedback devices usually apply user-grounded forces to the fingertips that try to mimic the cutaneous interaction forces that occur naturally during interactions with an object or environment. The examples skin deformation devices shown here are all wearable on the fingertip and provide multiple degrees of freedom of skin deformation feedback. All these devices apply normal forces to the finger pad, while some can apply shear, some can change the contact location or contact angle with the finger pad. All these devices have been shown to be a very compelling replacement for kinesthetic force feedback. This is because skin deformation is a natural component of manipulation. So for instance, when I hold this pen, which some of you may not be able to see, I can feel the skin of my fingertips deforming. These skin deformation forces occur naturally and are very useful for fine manipulation tasks. The skin deformation device that we have in our work has a delta parallel mechanism to achieve 3 translational degrees of freedom. A bias spring tether transmission allows the motors to be placed out of the way on the backside of the finger pad, or backside of the finger. We cover the end effector, the part that makes contact with the finger pad, with a gecko-inspired dry adhesive developed in Mark Suchoski's lab at Stanford. This allows us to render large shear forces this allows us to press lightly on the skin and still generate large shear forces. We use a magnetic tracker mounted to the finger interface to track position and orientation in 3D space. Our skin deformation devices are position controlled, so we must convert interaction forces we want to render into positions using an estimate for finger pad stiffness. We interface our devices with Chi3D, which is a haptic rendering and virtual environment framework, which should be shown here. Chi3D uses a proxy point algorithm to calculate the interaction forces between the device and the virtual environment. Proxy point algorithm uses 2 virtual points. One point represents the actual position of the haptic tool, which in our case is the user's finger. This location is read from the magnetic tracker. The other point, the proxy point, represents the location of our virtual finger. The proxy point always attempts to move towards the haptic tool position. When the haptic tool comes in contact with the virtual object, the real finger penetrates the virtual object, while the proxy point is constrained to the object surface and attempts to minimize the distance between itself and the real finger position. When a local minimum is reached, a force is calculated using a virtual spring between the proxy point and the real finger position. This interaction force is used to update the dynamics of the virtual object and is also displayed to the user through the haptic device. Okay. A challenge for haptic rendering using skin deformation devices is that these devices are prone to saturation due to limited motor power and lack of world-grounded force feedback. This means there is nothing preventing the fingers from moving closer to one another after we've maxed out the amount of skin deformation that we can render. Furthermore, this means we're limited in the amount of virtual weight that we can render to a user when they lift a virtual object. We wondered if there was a way we could increase the perceived weight we are able to convey using skin deformation feedback without radical changes to hardware. There's been some prior work on enhancing perception of physical properties of virtual objects. The proxy point algorithm mentioned before is a very common one. By not allowing the visually displayed virtual finger, or the proxy, to penetrate the object's surface, the object is perceived as being stiffer than if the finger was allowed to penetrate the surface. Another perceptual enhancement is the display of vibrations upon contact with the virtual object. This also increases the perceived stiffness of the virtual object. These methods are effective for stiffness, but cannot be used to enhance perceived weight. A paper by Lecour et al. Showed that by changing what's known as the control to display ratio, we can both increase and decrease the perceived weight of a virtual object. For example, we track the user's hand when they pick up a virtual block. We can scale their movements in the virtual environment such that it shows the virtual hand moving less than the user's actual hand, which they cannot see because they are wearing a VR headset. Due to this change in only visual rendering, the user perceives the object as being heavier than an object without scaled movement. We wondered if there was a way to increase the perceived weight of a virtual block using skin deformation cues, as these methods could be combined to create a more compelling virtual environment. We decided to try scaling the inertial forces of a virtual object. This idea is that scaling inertial forces will allow us to convey more virtual weight by using the motion of the virtual object and the horizontal degrees of freedom of the haptic device, without requiring significantly increased power and forces in the vertical direction. To do this, we increase the virtual mass of the object by a scaling factor, SF, and decrease the virtual gravity by that same scaling factor. As you can see, this keeps the virtual weight of the object the same. But there's a subtlety to this trick. As anyone in the audience who may have walked on the moon might know, objects fall slower when they are lower than Earth's gravity. Therefore, we need to revert the virtual object's mass and gravity back to their original values when the user is not in contact with the object. To understand and accentuate the effect of scaled inertial forces, we use a grasp, lift, and place task. A grasp, lift, and place task is a common manipulation task where the horizontal motion elicits inertial reaction forces in addition to the vertical inertial forces and weight of the object. For all our grasp, lift, and place tasks, the virtual block started on the right-hand side of a virtual table. The block was grasped, lifted up and over a virtual wall, and placed on the left-hand side of the virtual table. In this example that is not playing, we would have seen the reaction forces that are being commanded to the skin deformation devices for two cases, one being no scaled inertial forces, or an SF equal to 1, and one for a scaling factor of 5. The components in the horizontal direction of motion are larger for the scaled inertial forces since the object has more mass, while the forces in the vertical direction remain the same because the object's weights are equal. This larger horizontal component is what we hypothesize will affect the user's weight perception. We apply this algorithm to our skin deformation device and performed a human subject test to show that scaling inertial forces influences virtual weight perception. There are two parts to our study with a total of 11 subjects. The first part of the experiment was an open response paradigm. The purpose of this open response paradigm is to understand the subject's beliefs about what they're feeling. Instead of asking subjects questions about the perceived weight, we asked subjects to describe, if any, differences between two blocks that they explored in a virtual environment. The subjects had no idea how the rendering of these blocks were different. The blocks were of equal weight, but one block had scaled inertial forces with a scaling factor of 3. We presented the blocks sequentially and asked subjects to grasp, lift, and place the first block on the other side of the small virtual wall before alternating to the second block and repeating the task. Each block was presented multiple times before subjects were required to answer, and the order of presentation of the blocks was pseudo-randomized across participants. The results of this portion of the experiment are promising. 9 of 11 subjects responded that they felt the block with scaled inertial forces felt heavier. 1 subject said that they felt that the block with scaled inertial forces felt bigger, and 1 subject said that they could not detect a difference between the 2 blocks. The second portion of the experiment was a more traditional weight discrimination task, which consisted of 40 training trials and 2 sets of 50 experiment trials, using a 2-alternative force choice paradigm. Each trial consisted of a reference block and a comparison block, presented in a pseudo-randomized order. Subjects were asked which block felt heavier, and their answers were recorded. The training trials were rendered using standard gravity with no scaled inertial forces, while the experiment trials used scaled inertial forces to render the comparison block. Scaling factors of 2 and 3 were used for this experiment. All trials used a reference of 200 grams, and we chose comparison weights to be equally distributed across a range of masses and weights that we could realistically render on our device. Each comparison weight was presented 10 times in a pseudo-randomized order. We took the responses from the weight discrimination task and plotted the percentage of trials in which the subject felt the comparison block was heavier against the comparison weight for each scaling factor. In this sample plot for a single subject, the subject thought that 125 grams with a scaling factor of 3 was heavier than 200 grams for 1 out of 10 trials, or 10%. We then fit a psychometric curve to this data using a sigmoid function. Using this curve, we calculate the point of subjective equality, or PSE, by taking the comparison weight corresponding to a 50% heavier response on the curve. The point of subjective equality in this case represents the value of the comparison weight with scaled inertial forces that subjects feel is equal to the reference weight. We found that the point of subjective equality for each subject, except for 1. We could not fit a psychometric curve to the data of the subject who could not detect a difference between the 2 blocks in the open response portion of the experiment. We then averaged the PSE for each scaling factor across all subjects and plotted them as shown here, with error bars representing plus and minus 1 standard deviation. We found that the average PSE for each scaling factor are statistically significantly different from both the reference weight and each other. This shows that scaling inertial forces has an effect on virtual weight perception, and that this effect varies with the amount of inertial scaling. In conclusion, we used a 3-degree of freedom device, force feedback device, to convey skin deformation cues in lieu of kinesthetic cues to convey object mass properties to a user. We scaled the inertial forces of a virtual object by increasing the mass and decreasing virtual gravity. We ran an experiment where we first used an open response paradigm to determine that subjects interpreted blocks with inertial scaling as being heavier than blocks without inertial scaling. We ran an experiment where we first used an open response paradigm to determine that subjects interpreted blocks with scaled inertial forces as being heavier than blocks without scaled inertial forces. The findings allow us to expand on the range of weights that we are able to convey in virtual reality using skin deformation feedback devices. We then performed a more traditional weight discrimination task and measured the significant effects of scaled inertial forces on weight perception for 2 different scaling factors, showing that the effect varies with the inertial scaling factor. Going forward, we would like to investigate the combination of scaled inertial forces and control to display ratio to see if the effects can be combined. If they can be combined, we would like to know if the effects are additive and how users' perception varies if these methods are in conflict with one another. Thank you.